How on earth can face recognition systems identify you if they have just one photo of you? Today, we'll learn one-shot learning. How AI can learn to recognize something if it only has one example of it. I'll also show you how easy it is to make a simple one-shot learner. Let's say you have a traditional AI system that wants to differentiate cats and dogs. You can provide the system with many photos of cats and dogs so that it learns their common features. For example, cat faces tend to be rounder. But what if you're designing a facial recognition system for office entry? That's an entirely different game. It's not practical to take hundreds of photos of each employee. It's even harder when an employee hair lengths, hairstyles, and makeup change over time. So how can computers recognize faces? Let's say you wanted some objective criteria for whether two photos are of the same person. You might look at features like eyebrow thickness, nose length, eye color, and so on. Then you would calculate the values of those features in each photo and compare them. One good way is to subtract one from the other and take the square. There are many benefits to taking the square. For one, big differences will become even bigger. You can then average the numbers. Give more weight to features where small differences make you think a photo is of a different person. Think of the average as the distance between both photos. If the distance is below a certain threshold, the people in both images appear similar. So you can conclude that they are of the same person. If the distances are above the threshold, you conclude they are of different people. And that's the essence of how AI learns to recognize you even when it has only one photo of you. But how can an AI algorithm calculate a person's eyebrow thickness from a photo? For things like images, we often use a model called the CNN, or Convolutional Neural Network. A neural network is a structure inspired by the human brain, and a CNN is a special kind of neural network for images. A CNN has so many squares, you may feel like you're at a tile factory. But it's actually surprisingly simple. When a CNN is fully trained, the lower layers of the network detect simple features like the edges of the face. Once you know where the edges are, you can detect more complicated things like the eyebrows. Then you can calculate how thick the eyebrows are. Let's zoom into one piece of the puzzle, detecting the edges of the face. Let's make our picture black and white and low resolution for simplicity. White pixels have a value of 1 and black pixels have a value of 0. Here's what you can do to detect vertical left edges. Is there a left edge at the pixel I've highlighted in blue? Let's center a set of 9 numbers over that pixel. We'll call the set of numbers a matrix. Let's color code the numbers based on their values. Multiply each number in the matrix by the value of the pixel underneath it. Then sum the numbers. In this case, you get a negative number. Why? The negative numbers are multiplied by 1, while the positive numbers are multiplied by 0. By the way, the multiplication process is called a convolution. It gives CNNs its name. What if I were to do the same thing on the right edge? I get a positive number as I'm multiplying positive numbers by 1. And if I were to do the same thing on a completely black space or a completely white space, I would get 0. In one case, I'm multiplying everything by 0. In the other case, the positive and negative numbers cancel out. So here's one way of distinguishing between a left edge, a right edge, and everything else. If you wanted to detect horizontal edges, rotate the numbers clockwise. When you've found the face edges, it's easier to find things like the lips. Then it's easier to find things like lip size. The CNN ultimately outputs an encoding. In other words, a set of numbers. Each number describes a key feature that differentiates one face from another. They may or may not describe something intuitively recognizable to humans. But if you spend enough time looking at them, you can often assign some meaning to them. I've described a fully trained network. But how do we train a network? And what does training a network even mean? When you're training to get good at darts, the objective is to hit a bullseye. You first throw some darts. If you hit to the left of the bullseye, you try to control your muscle movement so your next hit is a little to the right. If you hit a bullseye, you try to repeat your technique, and so on. And that's a good analogy to training a neural network. Here's what a bullseye looks like. Let's say I provide you with 3 images. 2 database photos of person A and B, and another photo of person A. We want the distance between the 2 photos of person A to be low. In particular, it should be lower than the distance between this photo of person A and the photo of person B. And in practice, we would have a safety margin. If you've achieved that, then you've hit the bullseye for that triplet of pictures. But if not, you've exceeded the safety margin by the distance between your shot and the bullseye. One best practice is to make sure that person A and B look similar, rather than completely different. That way, your AI machine learns to distinguish between people that look similar. And how can you get better at hitting bullseyes? Earlier, I showed you an edge detection matrix. Let's say the total must be at least 1 before you classify something as a right edge. Then this is a right edge, but this isn't, because the total is only 0.75. However, if I were to double the numbers in the matrix, then the total would now be 1.5. So it will be classified as a right edge. So making the numbers bigger allows you to detect more edges. Some of these edges will be face edges, but others will be unwanted edges, like the edges of a door. When you work on lots and lots of triplets of photos, the accuracy could decrease or it could increase. But if I made the number smaller, I'll detect fewer edges. My accuracy will again change based on the ratio of wanted to unwanted edges. So I'll try many sets of numbers in all my matrices, and I'll pick the set of numbers that allows me to hit bullseye as often as possible. More precisely, I want to exceed the safety margin by as little as possible on average. That's what training a network means. And to complete the darts analogy, each set of numbers is a muscle movement. Different muscle movements cause the darts to land in different places. Let's recap what we learned. Here's how AI can recognize someone based on one photo. First, it learns the key features that distinguish one face from another. For any photo, it can express the key features as a set of numbers. It then examines how different the photo is from the person presenting themselves. The distance metric can measure the degree of difference. A convolutional neural network is a great tool to process images. When one-shot learners use images, they need millions of pairs of photos to recognize someone based on one photo. But I'll show you how to create a simple one-shot learner. Let's ask ChatGPT to create a one-shot learner. I pasted ChatGPT's output into a Google notebook that can run code. ChatGPT did a fantastic job. I only edited a few lines. If this were a work project, I would edit more code, but it would do as a simple example. This portion of the code creates the one-shot learner. This portion trains the one-shot learner. This portion evaluates the accuracy of the trained one-shot learner on an outside dataset. Here's the dataset that trains the model. You can think of the right-hand side as representing people. So you have person A, person B, person C, and person D. And the left-hand side has numbers that describe the people. So you can imagine that person A has a big nose, person B has a big mouth, person C has big eyes, and for D, nothing is big. And we have one additional photo of persons A and B. Of course, I changed the numbers slightly. And here's the dataset that will evaluate the one-shot learner's accuracy. You can think of these as completely different photographs of persons A to D. Now let's run the code. The one-shot learner's predictions were all accurate. Most importantly, it correctly identified person C and person D, even though it only saw one photo of them. And it only took a few seconds. I hope you enjoyed the video. Let me know if you want to see more of such videos.